My name is Gerlinde Emsenhuber, and I'm going to present our work on mobile eye perspective rendering for optical see-through head-mounted displays on behalf of all authors. So, what is this about? Imagine that you have smart glasses with an AI assistant, and this assistant helps you in navigating everyday tasks, for example, interacting with an unfamiliar control panel. So what could happen is that you look at the control panel and the assistant highlights the next button that you should press. But what might happen in reality without using high quality eye perspective rendering is that you see something like this, where the virtual outline is badly misaligned with the real control panel. So why does this happen? Because the built-in HMD camera sees one view of the scene, while the user sees another view of the scene through the display. So whenever we try to derive virtual cues directly from the built-in camera, we have to make sure that it becomes properly aligned with the user's view. And this is where eye perspective rendering comes into play, because eye perspective rendering is concerned with reconstructing the user's view through the HMD by using the camera view, but also any other available sensor data, such as depth maps or maybe eye tracking. So at this point, I'm going to show you two videos to make you see what this looks like. We filmed through the display of the HoloLens 2. We extracted edges from the camera image, and we used eye perspective rendering to overlay those edges over the real scene. So in the first video, the eye perspective rendering method is of poor quality, and I hope you can see that the outlines are badly misaligned with the calibration target in the background. And in the second video, we use the same calibration target, but we use a better eye perspective rendering method, and now our outlines are much better aligned than before. Filming through the display like that has some serious limitations. First, the quality of the recording. Second, we cannot run the eye calibration on the camera. And third, we cannot use eye tracking. And since eye tracking is an important part of the rest of our paper, I am now going to switch to synthetic images for the rest of my presentation to illustrate my points. So, use cases. Where might we use this combination of camera-derived virtual cues and eye perspective rendering? First, in repair and assembly tasks, an assistant might highlight the next tool or part that you should use. And of course, if the highlight is misaligned, then the user might pick up the wrong tool or part. Then another use case is text augmentation. For example, highlighting street signs when navigating in an unfamiliar environment. If the virtual text is misaligned with the real text, then both will probably become unreadable. And third, color correction. For example, for people with color vision deficiencies. In that use case, the pixel correct display of the overlays is just crucial for it to work. So we implemented 3 techniques on the HoloLens 2 and made a user study with them, but first the 3 techniques. So the first one is the plane proxy. This is a technique that is commonly used in AR applications. So with this technique, you take a plane and put it at a fixed distance in front of the user. And then you project the camera image, or in our case, the virtual cues that are derived from the camera image, onto this plane using projective texture mapping. And you render the plane from the point of view of the left and the right eye. So this doesn't work if the scene does not fit the plane as is shown in this case. So you can see in the image what's happening. The virtual outlines are misaligned over the entire field of view because the real scene does not match the plane at that distance. The second method is the mesh proxy. Here we use a spatial reconstruction of the scene and then proceed as before. We project the camera image on top of the mesh. This creates good alignment if the mesh is precise. So in this method, the alignment quality is related to the quality of the mesh reconstruction. And then third, our novel gaze proxy approach, where we again use the plane, and we also use eye tracking, and we move the plane to the user's fixation point. So you have the same issues as with the proxy plane, that if the scene does not fit the plane, you have misalignments, but because we move the plane to the fixation point, you will have good alignment at the point where the user is currently looking. And as our study results will show, for many tasks that is good enough. Yeah, so we performed the user study to compare these three methods. It was divided into two phases. Phase one, we were interested in comparing the three methods, plane proxy, gaze proxy, mesh proxy, with respect to metrics like task completion time and accuracy, also with respect to ease of use and perceived workload. The second phase was more open. There we were interested in getting feedback from the users about the methods, about acceptance of the technology in general, and we allowed users to freely switch between the methods, but more on that later. So in phase one, participants were sitting in front of a checkerboard. They were watching the checkerboard through the HoloLens, and we highlighted one particular square and displayed the outline on the HMD. And the task was identify the highlighted square and press it as quickly as possible. There were two independent variables, obviously the eye perspective rendering method, and also for the checkerboard, the orientation, as we were interested in the effects of the viewing angle. For each combination of eye perspective rendering method and checkerboard orientation, the user had to repeat this press the correct square task 25 times. Results. In terms of accuracy and task completion time, we find that the mesh proxy and the gaze proxy significantly outperform the plane proxy. The mesh proxy still outperforms the gaze proxy also significantly. In terms of ease of use, users felt that mesh proxy and gaze proxy felt easier to use. In terms of workloads, they felt that the plane proxy increased the perceived workload. We also asked the users to rank the three methods based on subjective preference. Here the mesh proxy was ranked as the first. With the gaze proxy as a close second, there were a lot of instances where the users could not make a decision and said both are tied for the best method. What is consistent is that the plane proxy was ranked as the worst method. And in the second phase, like I said, the more open-ended phase, we simulated the low vision support system. We extracted edges from the camera image and displayed these edges all over the field of view. Participants in this phase were allowed to switch between the three methods. We also gave them an explanation of how they worked. For the plane proxy, we gave them the option of adjusting the plane distance, so they could move the plane distance closer towards them or farther away. And then we encouraged them to try out simple tasks like building with Duplo blocks and reading. And the feedback that we received was that mesh and gaze proxy felt much more natural than the plane proxy. Our participants really did not want to use the plane proxy, even when they could adjust the plane distance. In terms of acceptance, our participants noted the potential of such an application for navigational tasks and also for assembly tasks. There were also some criticisms about the implementation, for example, about temporal coherence of the edges. So this highlights the need for stable image analysis for such a use case. Yeah, so that was the study. So, conclusion and key insights of our study. We find that it is possible to implement both the gaze and the mesh proxy method on current state-of-the-art HMDs with the high precision. So in the second phase, when the participants were seeing the outlines, we asked them to estimate the offset between the outlines and real objects. And at a distance of 75 centimeters, it was estimated that there was 1 millimeter offset for both methods. So not pixel precise, but very good precision after all. Second, we find that the gaze proxy method is an effective alternative to the mesh proxy method. It ranked comparably to the mesh proxy in terms of accuracy, in terms of ease of use, in terms of workload. There is only, in terms of task completion time, there is a minor issue that probably needs further investigation. It is simpler to implement as it does not rely on a mesh reconstruction. It causes less battery drain and heat, which is important for mobile devices. And what we also found in the study is that eye tracker latency can be an issue with this method and should be further investigated. And finally, we find that the plain proxy is unsuitable for practical use cases, as it just does not work. It was ranked as the worst choice of the three methods. It was the worst in all metrics. In the phase 2 of our experiments, participants switched away from this method as soon as they had the option to, and they did not want to use it. And they reported cases of double vision when using this method, indicating that depth perception is compromised when using this technique. In conclusion, we find that this combination of deriving virtual cues from the camera image and using eye perspective rendering to display it is a powerful technique that should be further investigated. And we release our implementation for the HoloLens 2 of the three methods as open source. You can find the link in our paper or on the slides. So that is the end of my talk. Are there any questions?
Questions for the speaker?
Any questions? Okay.
Thank you for the great talk. So in your evaluation, so the object is fixed, is static, the object?
I did not entirely, so you...
For example, like the object, right, you try to overlay the virtual information on top of the object, right?
Yeah.
So the object is the virtual, the object always like static there?
The object was static, but the user was allowed to move.
Allowed to move,
Yeah.
I see. So, so then how do you evaluate the task completion time?
Well, the users were sitting, and we measured essentially when we displayed the highlight on the HoloLens. And let's see if I can go back to that slide. You can see that there is a frame around the checkerboard here. So that is a touch frame. So we essentially recorded the time when we displayed the highlight, and we recorded when there was a touch, and that was our task completion time.
Okay. And in your evaluation, you also have accuracy, right?
Yeah.
So the accuracy, it defines like the user successfully complete the task, right?
Did the user press the correct
So how about the absolute kind of like tracking error? Is there any displacement like that? The errors?
I did not.
So for example, you overlay the virtual information on top of the physical one, right? So, but that may not be exactly matched, right? So then how do you define it's completely like it's successful? Depends on the user. Okay, okay. Thank you.
Okay, so any other questions? Just stand your hand.
Other questions? I'll actually ask one question. So, what is the overall reason why plain proxy performs so badly? What's the highest level?
Because it's usually it just doesn't fit the scene geometry.
Okay.
So even if you manage to adjust the plane to the current scene, which can be done, once you move your head or you move even a little bit, it will just be off again.
Okay.
Okay. I said even if the user adjusts the plane correctly to the task, for example, at working distance. As soon as they move their head a little bit, it will just be off again. So that's the reason why it just doesn't perform good.
Any other questions? Okay, let's thank the speaker once again. Thank you.
All right, so hello everyone. I'm Bin Li, I'm associate professor at Penn State. So this is the joint work with my PhD student Jiangung Chen and Mingyi Zhu, who equally contribute to the work. And Jiangung recently joined the Meta Reality Lab. So we already know that mixed reality basically merge the physical and digital worlds, allowing the interactive interactions between the virtual and physical world. And it has many applications, such as manufacturing, education, and training. So for example, in our earlier work, mixed reality-based firefighter training, so the users is able, with a mixed reality headset, is able to visualize the fire and extinguish the fire in the real environment. So the system significantly enhance the preparedness for the firefighters. So the corresponding work actually was published in InfoCon 2023 and won the Best Demo Award. So another application is mixed reality aided collaborative operation. So here is the Alex viewport, and this is the Bob viewport. So Alex can follow the MR guidance to place the physical Lego piece on top of the virtual piece. So this is really like very intuitively guidance without consulting to the manuals. And in addition, Alice can also see the Bob progress as if they work side by side. So it significantly enhances the seamless collaborations. So the corresponding work was published in InfoCon 2022 demos. So in this work, we are interested in MR-aided operations. So in such application, even with the MR assistance, human operators can still make mistakes. So we may slightly kind of like place the physical brick just next to the virtual brick, right? So I mean, we are all human, or sometimes make mistakes, right? So the question is, can an MR system automatically detect whether the user is really following its guidance to help prevent the human errors? So specifically, we are interested in the MR intelligent systems that can monitor the user's action in real time and provide the feedback or corrections. So here, the first challenge lies in the discrepancy between the virtual and physical objects due to the imperfect 3D modeling and lighting estimation. For example, this is a virtual Lego piece. I hope that you can listen my voice. So this is a virtual brick, and this is a physical brick, okay? You can see that even for the same pixels, pixel values are significantly different because one is virtual piece, one is physical piece, right? So the prior method for the similarity check, right, based on the pixel level similarity check, is very sensitive to the noise and illumination. So in this work, we use the semantic level comparison. In particular, we use the randomly parallelized and learning-based segmentation to generate a mask for virtual and physical objects and compare them based on object shape instead of the pixel levels. So the second challenge lies in the dynamic MR users' behaviors, making it difficult to capture the frame in proper time. So for example here, right? So once after the user put the physical piece on top of the virtual piece, so we need to capture the frame, right? But if we capture the frame so early, then we capture the frame actually with a human hands here, right? So that's not what we want, right? And then if we catch it too late, then it will affect the end-to-end latency, right? Performance, right? So for that, we use the hand. We developed the lightweight hand detector to facilitate the hand movement detection. Another challenge is that because our human head always like move around, right? So the capture frame may not be aligned with the left lung funk, right? So we need to leverage it, the tag-based approach to align the frames. Okay. The previous speaker actually also developed some other method. I think that can be also used in this scenario. So to sum up, we developed the system called EVER, which consists of the client side on the smartphone. We implement on the smartphone. And another part is that we also implement the module on the server. Right? In addition that, we implement 4 different Lego models, 4 different, basically the Lego shapes. And on the client side, we basically on the smartphone, we developed the automatic motion detection. So when the so here actually we for the virtual blick we capture the left frames, okay, and then we need to detect when the hands move out, and then we capture the target frame that consisting of the physical blick, okay. So here is just a lightweight hand detector, so you can refer to my paper for details. So I think this part is standard. And then we also developed the tag-based localization. So on the client side, we need to do the frame clipping, scaling, and encoding, and then send the pictures to the server side for decoding and alignment. Alignment is basically like for we randomly sample few key points, okay, and then do some transformation to align the frames. So this is also quite standard in the CV. So on the server side, so we got 2 figures. One is the left frame, another is target frame, right? For the left frames, we use the rendering pipeline to extract the virtual piece and then generate the mask. And then for the targeted frames, we train fine-tune a Euro model to detect this shape, and then apply the binary filter to generate this mark. And then we check whether the class of the virtual and physical piece exactly match. If they match, then we calculate the intersection over unions between the mask of the class labeled and applies an appropriate threshold. Okay. So this is our demo.
If the user follows the virtual guidance, the system proceeds to the next step. Otherwise, it remains on the current step.
So this is just show how the system works.
If the
And we also conduct the collect the customized Lego dataset. We use the Google Pixel 6, the Android phones, and then capture our Lego dataset through the various heights and orientations, and under various kind of like lighting conditions, because in our lab we can tune the lighting conditions, and we collect enough like data samples to demonstrate that we collect enough data sample. We use the learning curve to make sure our amount of data that we collect is sufficient to train to fine-tune our Euro model. Okay, I think this is actually to justify that. I think you can see that about 150 samples is sufficient to fine-tune in our this small applications, and we collect more than 200 training samples. Also, to generalize our approach, so we also evaluate our approach in other PCB image data set collected by Florida Institute for Cyber Security Research and Blackboard data set. So you can see that. So overall, and also we compare our algorithms with other two baselines. One is the symbol, so compare the frames based on pixel values. Another one is just like with limited semantic comparison is that we extract the embeddings with euros, like some features, like the edge, all these kind of features, and calculate the cosine similarities. So you can see that actually we evaluate the three different data sets using the receiver operator characteristic. This is the false positive ratio. This is the true positive ratio. And you can see our approach is the blue one, actually significantly better than the two other baselines. And also in terms of the accuracy, we plot the accuracy with respect to the threshold. The threshold for the IOU actually comparison. So try to see how much they overlap. So that is, you can see when the threshold is selecting like 0.5, our performance is achieve very high accuracy, above 90%. We also conduct the system level evaluation. So because we implement our application on smartphone, we don't want to consume too much additional resources. And from here we can see our end-to-end evaluation is about 80 milliseconds. So significantly lower than the human reaction time, which is about 270 milliseconds. Obviously, the cost is about we require a little bit higher inference time, but this is the end-to-end latency still far less than human reaction time because it guides our human operation. As long as far less than human reaction time, you don't even notice. And then the performance, like we also compared with that without auto verification. We can see that with the auto verification, the average CPU usage and memory consumption, and as well as the average power consumption of the smartphone, is just slightly higher than the corresponding like baseline that without auto verification. So to sum up, our work is closely related to three pieces of work, like the first one is the auto verification, which is widely studied in the programming language. So typically, you know, when you like program Python, like we have an automatic check, right? And also the image classification and similarity check. And there are also some prototype MR80 operation, but they don't study the auto verification part. And also we use the edge assisting mobile design, try to ensure the end-to-end performance is desirable, right? So the main limitation of work is that so far we just consider our system the object operation. The object we manipulate is all rigid object. It'll be interesting to also extend it to the work to non-rigid object. And also for new tasks, not just Lego operation, but maybe other new tasks, we request the task-specific reference images, okay, which introduce the setup overhead. But this is just one-time effort. One potential idea is to integrate the large language models, maybe to reduce the setup effort. I also attend several talk about the large language models, vision language models to generate the guidance. I think that's also interesting, maybe extension. Obviously, another is robustness under the severe occlusions, maybe like the camera is blocked or extreme live viewpoint. So to sum up, we present the EVER, a unified and extendable framework for end-to-end fully automated verification in mobile MR80 operating tasks. Okay, I will stop here.
Thank you, speaker. Questions for the speaker?
Any question?
Yeah, thank you for your talk. This is Yanming from Duke University. So I think your work is pretty meaningful because it allows the XR system to not only instruct the user to do the task, but also keep an eye on to monitor the user's performance. So I think my question is, you mentioned that you have the plan to move on to other tasks other than just assembly. And you mentioned that probably you can have some large language models to in the system. So I'm not sure, do you have the plan for like specific tasks? Yeah.
So actually, this is basically for large language model to generate the instructions, right, like guidance, right? I think the main challenging is that the large language model can generate like incorrect guidance. You don't even know it, right? But I think the good thing of large language model is that it generates some guidance, and then you can review, right? So that can significantly reduce the setup time. Yeah, in that perspective, right? But the expert need to review it. Yeah, yeah. Otherwise, it doesn't make sense. If you directly follow the MR, the large language model generated guidance, right? I mean, you make because this kind of work typically for the entry level workers, right? So they don't even know whether the guidance is correct or not. They just follow it, right? Especially also for students doing the lab, right? So they just, right? So it's bad, but the large language model can significantly reduce the setup times. Yeah.
Any other questions? Okay, so I have one question. So I just want to know, because I'm also working with the marine biology side, and I want to know that in the LLM, basically what you explained about that, so can we use the whatever the resultant output you are getting and the iteration process, like whatever result you are getting that, and you can do the iteration process the same model. Okay, this is the correct, someone will review it, and after that will get that, okay, this is the correct image, and after that we can do the iteration, so it can be improvised that process, and it could be possible that way to be much more near to be accuracy.
Your question. So for the large language model, basically you generate some a sequence of steps, right? And then for the expert to review it, right? And then later on you can deploy that on the system. Yes.
And you can do the iteration process.
Yeah, exactly. But right now, this kind of step is predefined. Yeah.
Okay, thank you.
Yeah.
Okay, let's thank the speaker once again.
Hi, so as I was introduced, I'm Kristen from Carleton University, and I'll be presenting mine and Rob Tether's work on complex interactions in smartphone-based VR. So XR technologies are increasingly being used across industries and for work, learning, and personal use, and it's becoming increasingly important for people from all backgrounds to have access and experience using spatial displays. However, its high price point presents a significant barrier to access, as modern VR displays cost upwards of $500 USD. Meanwhile, mobile VR breaks this financial barrier to access by integrating a smartphone into a plastic or cardboard viewer to support low-cost VR experiences. This solution is worth exploring given the large majority of the population own a smartphone, regardless of income or education level, and mobile VR devices have been widely adopted. For example, a 2023 survey of 300 people found the majority of VR hardware owners only own mobile VR devices and not high-end hardware, so not a Quest, for example. However, mobile VR does not support 6 degrees of freedom interaction, which is often required for VR applications and immersive experiences. In VR, interactions are commonly performed using fully tracked controllers. So these controllers are needed to support common interaction techniques, including ray-based pointing and virtual hand interaction. In mobile VR, selection is commonly performed using head gaze pointing, where the user's head, tracked in 3 degrees of freedom, controls a selection array. To confirm selections, a button embedded into the headset is typically used, or a dwell time, given not all mobile VR headsets include a button. In order for mobile VR to effectively be an affordable alternative to high-end VR, its limited interaction support must be addressed. As such, we proposed the cardboard controller, a 6-DOF tracked handheld controller. The design keeps cost and convenience at the forefront. So 3 paper cubes are attached to a cardboard handle and tracked by the smartphone camera to determine its 3D position. We conducted 2 user studies to evaluate the selection performance of the controller using popular selection techniques. So in the first study, we compared different selection activation methods as an alternative to the cardboard button, because it has known usability issues. And in the second study, we evaluated the selection performance of the controller using different selection techniques and compared its performance to head gaze pointing. For both experiments, we used a Samsung Galaxy S23 Ultra, a Google Cardboard with a 65-degree field of view, and the cardboard controller. Both studies had a within-subject design and employed the standard ISO selection task based on Fitz's law. The selection task includes a ring of targets. Targets are selected one at a time, and selections are evenly spaced apart. Fitz's law quantifies human performance using throughput, which is measured in bits per second, and throughput is based on the task's index of difficulty, denoted by ID. ID quantifies the task difficulty. Essentially, a higher ID signifies a more difficult selection task. We use effective measures in our ID calculations, and the full details of how we did so are in the paper. Both studies had the following independent variables. So 6 IDs ranging from 2.98 to 4.7 bits per second, 7 targets in a given target ring, and all IDs were repeated twice under each condition. The order of ID was randomized for each participant, but the condition order was counterbalanced according to a Latin square. In experiment 1, the unique independent variable was selection activation method. So we compared 3 methods. First is instant, where a target was instantly selected upon the ray touching it. Then dwell, where a 300 millisecond dwell time was used for selection. And then what we call marker, which is our proposed method, where the user holds a cardboard piece in their left hand, and it has 2 tracked markers attached to it. So to trigger selection, both markers must lose tracking by being moved out of camera view in some way. So the animation in the bottom right demonstrates this technique. So those purple cubes represent the selection markers. When they're hidden from the camera, the cubes disappear, and that is when a selection is able to be triggered. We recruited 18 participants, ages 18 to 44. 252 selections were recorded per participant, and we recorded the same metrics for a given selection in both studies. And those include selection time, throughput, target reentries, selection distance, the amount of time the controller lost tracking, and the number of times the controller lost tracking. And given the time constraints of this presentation, I will focus on the results about selection time and throughput, but of course the full details of all analyses are in the article. Regarding selection time, the marker method was significantly slower than dwell. We suspect this was partially due to participants' arm movements being more cautious when using the selection piece in their left hand. Given that it was an unfamiliar technique and it's made of more fragile paper materials, so participants didn't want to move it too quickly out of camera view, resulting in slower actuations. We modeled the relationship between selection time and ID and found it highly linear for all conditions. And this signifies that Fitz's law accurately applies to the cardboard controller. Dwell had significantly higher throughput scores than marker. On average, dwell had a score of 1.8 bits per second, while marker had a score of 1.1 bits per second. But past studies evaluating similar ray-based techniques reported throughput scores ranging from 1.5 to 2.5 bits per second. And the cardboard controller does fall into this range when used with dwell time for actuation. Regarding tracking accuracy, the controller lost tracking significantly more using the marker method, and we suspect this is partially because users had to simultaneously track two objects at once in a constrained 65-degree field of view, so tracking the controller and that selection piece in your left hand. And we also believe that contributed to the slower selection times for marker. Moving on to experiment 2, the unique independent variables were selection technique and target depth. So we compared 3 selection techniques: head gaze pointing, ray casting with the controller, and virtual hand selection, where users reach out with the controller to touch the targets. All selections were actuated using a 300 millisecond dwell time for the second study. And we placed the selection tasks at 2 depths, one within reach and one out of reach. So the out of reach depth was the same depth, the same target depth used in the first study. So we were able to directly compare certain results between both studies. And the 5 study conditions are made of the selection technique and target depth combinations, except the virtual hand technique couldn't be used with out of reach targets, so that combination was not included. We recruited 20 different participants for experiment 2, ages 18 to 45, and 420 selections were recorded per participant. Regarding selection time, head gaze was significantly fastest, and ray casting with out of reach targets was slowest. When only considering in reach targets, the virtual hand technique was significantly slower than ray casting. And like in study 1, we modeled the relationship between selection time and ID and found all conditions highly linear, again showing the Fitz's law model strongly applies to the data. The controller had average throughput scores ranging from 1.74 to 2.4 bits per second. Head gaze had the highest average throughput scores, but notably, ray casting with in-reach targets performed significantly better than ray casting with out-of-reach targets and the virtual hand technique. But no significant differences were found between the throughput scores of virtual hand and ray casting with out-of-reach targets. When looking at tracking accuracy, the controller lost tracking significantly more when selecting the out-of-reach targets. But regardless of selection technique, when the interactions were within reach, tracking was very reliable. And we noticed users more often moved their head with their hand movements during the in-reach tasks, which kept the camera, the smartphone camera, pointed towards the controller more often. And we believe this likely helped in maintaining tracking in those in-reach tasks. At the end of the experiment, we asked participants to rank each selection technique. Overall, head gaze was most preferred, followed by ray casting. Participants provided a rationale for why they chose their preferred technique. Participants who preferred ray casting over head gaze felt the controller was more intuitive and less fatiguing to use. One participant stated selecting with the controller felt more purposeful. Similarly, participants who preferred the virtual hand technique liked its interactive feel afforded from physically reaching out to the selected targets. And these positive responses further justify the importance of a 6DoF device for mobile VR that supports these immersive interactions that users enjoy. And overall, Study 1 validated the controller as an input device for mobile VR, reporting comparable throughput scores to past similar pointing techniques. Study 2 further demonstrated the controller's ability to support popular selection techniques for in-reach tasks. And in general, the cardboard controller increases the complexity of possible interactions in mobile VR. Based on our findings and past related work, we proposed 5 guidelines for designing mobile VR input devices and interactions. So one is take advantage of the materials, including the smartphone, its inertial sensors and screen, as well as the cardboard surfaces. 2, creative solutions are needed to circumvent the unique design constraints of mobile VR. So cost, portability, and system limitations are larger design factors for mobile VR compared to high-end VR. As such, past research has proposed many creative solutions to accommodate these constraints. And 3, collect multiple streams of data and merge them to compute 6 DOF positioning. So for example, optical tracking, acoustic-based tracking, and inertial sensors can all be implemented by low-cost means and used in combination to increase tracking robustness. And 4, the design must be robust enough to work across a variety of environments, given mobile VR is meant to be portable. This means working in different lighting and noise conditions. And then 5, the processing capability and hardware specs of the smartphone must be considered when designing interactions. As well, alternative solutions like cloud-based servers to offload computational tasks should be considered if needed. Thank you for listening to my talk, and you can access the journal article using the QR code. Thank you.
Questions for the speaker?
Thank you for your talk. And it's very impressive to see that you can achieve such a great performance with such a cost-effective cardboard controller. My question is about in your design decisions, have you looked into which, like the size and the layout of those markers could provide you the most robust performance?
Yeah, so in my initial testing, it was a very simple one marker, just sort of proof of concept. And then when I got into this, I used Vuforia in Unity, so I was basing things off of Vuforia's best practices, where that's how I kind of made up the marker images. And I decided to do those 3 markers because it's also a 360-degree view where you can turn it around and stuff. And I've been told from people that use Vuforia often, it's actually better not to use a ton of markers and really overload the system. So it's kind of simpler the better. So that's why I chose to have the 3, and then I triangulate the center position.
Thank you.
Other questions? I'll actually ask a question. So your cardboard controls, so first of all, fascinating work. This is really cool. Won't you run into issues with longevity of the controllers? That
Yeah, I have noticed that because I've done some other studies, and then once a lot of participants are using it all day,
Yeah.
some of the pieces do wear out. But I have noticed, so right now, the current, I think it's on the next slide, it's a folded controller where you fold up the cardboard instead of it being a flat piece, so that helps with the longevity. And I also noticed when I was using a single layer of cardboard, it wasn't as good as when I simply put 2 layers on top of each other. It really, it made it last a lot longer with participants. But yeah, that is something to consider with the design.
fascinating. Any other questions? Okay, let's thank the speaker once again. Great work.
Thank you.